In this video, we're going to be talking about how to simplify a radical. So first, some important information that we need to know. Okay. If we have a radical expression, we have some square root. The nth root, we can have any number in where the n is. Usually it's 2. I know you've seen cube roots, but really we can have whatever number root is possible. But whatever number we put in there, that's your index. And then the actual radical itself. And then the radicand is what goes underneath. So if there is no index, which a lot of the times there's not, we assume that to be 2. Usually, when we talk about parts of a radical, or if we say like the square root of 16, we usually just deal with the positive numbers, and that's 4. There will be later in another math class, we'll talk about how that's not necessarily true, but we'll get to that later. Okay. So before we do anything, we want to list out the first 12 perfect squares. So if you're not sure how we're getting these numbers, we're taking 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, and so forth. And you could do that up to 20. Really, 12 is a good stopping point, but knowing more wouldn't hurt. All right, so let's do some of these examples. If you're given something that has a perfect square, so like the square root of 16, you know what that's going to be. 4, right? If you're given something like number 2, well, you know the square root of 121 based on our list, and I'm going to rewrite them. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. Okay. So 121 is a perfect square, and that's 11. So we can say the square root of 121 is 11. It's right next to the radical. So that means they're multiplying. So we can multiply these together to get 22. We do the same thing for 3. Now, 289 is not one of our perfect squares that we have listed, but that, because it's in this section, and it is a perfect square. If you're not sure what that is, you can go to your calculator. Go to your main screen. Ignore all of my... Type in the square root of 289 and press enter. So 17. So we know now that this is 6 times 17, and we can multiply that together to figure out what that is, which is 102. I could do number 4, but we're not going to do that. So that's what happens if you have a perfect square. Now what happens if you don't have a perfect square? This is what we're going to do. We're going to find the largest perfect square that the radicand, the number underneath the radical, is divisible by. We're going to break down that radical using this number. You're probably thinking, how do we do that? So we take the square root of the perfect square, take it out of the radical, leave whatever's left over underneath the radical symbol. So if we had an example like number 5, if you weren't sure, well, 1, if I look at my perfect squares, 32 falls in between 25 and 36, so I know it's not a perfect square. So then what you want to do is, and really you could do this 2 separate ways, so I'm going to show both. One is take 32 and start dividing it by your perfect squares. 32 divided by 1, well, we know that's 32, but that wouldn't change anything. 32 divided by 4, we know that's 8. Okay, so that might work. Let's keep going. 32 divided by 9, that's going to give us a decimal. We're going to avoid that. 32 divided by 16, that would work because that gives us 2. 32 divided by 25 would not work because that would give us a decimal. So we're looking for the highest number that would work, which would be 16. So we can say that this is equal to the square root of 16 times the square root of 2. 16 is a perfect square, and we know that to be 4, but 2 is not, so that would stay inside. So that's one way to look at it. The other way you could look at this is just think about your factors of 32. So let's say off to the side you had a little factor tree, 1 and 32, 2 and 16, 4 and 8. And that's it. So if you were doing it this way, let's say we know 2 and 16 work. Let's say we chose 4 and 8. Now, if you have a perfect square, you can go ahead and factor that. Like you know the square root of 4 is 2. But I can also break down 8 again, because 8 is not a perfect square, no, but it's not a prime number either. So unless these are prime numbers, it can be broken down. So prime meaning it can only multiply to be 1 in itself. So factors of 8, we have 1 and 8, 2 and 4. So we can say this is the square root of 2 times the square root of 4. Again, we know that the square root of 4 is 2. This is going to stay the square root of 2, and this is going to be 2. So that would mean we have 2 times 2 times the square root of 2, which would be 4 times the square root of 2. So you have the option to choose which one you feel more comfortable with. I will say that if you go the second route, depending on the numbers you choose, you may get bigger numbers. There's also this way. So let me show this real fast. So let's say instead of thinking about the square root of 32, you were just thinking about the factors. We can use 4 and 8 again. Besides 4 and itself, 4 and 1 and 8, 4, 8, 8 and 1. The other factors, for 4 we have 2 and 2. For 8 we have 2 and 4. And 4 we have 2 and 2. So you can think about it like this. Because we're dealing with the square root, we're looking for groups of 2. So if we have a group of 2, anytime we make a group of 2, those are the groups that get to come out of the radical. Anything that does not have a group to form, it's going to stay by itself. So all of your groups, so this is one group of 2. This is one group of 2. And then this one by itself stays underneath the square root. You would get the same answer, it's just a different way of looking at it. So let's do another one. I'm going to do it the last way and the first way, not really the middle way, but you could do it any of the ways. Okay, so 180. If I'm thinking of the different perfect squares, I'm going to start with 144. Now 144 is kind of unrealistic because 180 and 144 are so close. So if I were to divide this in my calculator that I'm holding, I get 1.25. So I know that can't work. 125 121 and 180 are also way too close, so that wouldn't work. I know I can't divide 180 by 100 and get a whole number, so that's not going to work. What about 180 divided by 81? You get a decimal, so that doesn't work. 180 divided by 64, another decimal. 180 divided by 49, another decimal. 180 divided by 36. That one gives us a whole number. So we have the square root of 5 and the square root of 36. The square root of 36 is 6, while the square root of 5 stays the same because it's prime. So we would have 6 times the square root of 5, and that would be our simplified answer. If we were breaking it down, 1, we would need to have some factors of 180. So 1, 180, 2, and 90. The bigger these numbers are, the more factors you're going to have. So I'm going to list them all first, and then I'm just going to pick a random one. 3 and 60, 4, and 45, 5 and 36, 6 and 30, 9 and 20, 10 and 18, 12 and 15. And those would be all of my factors. So the closer these numbers are, or if you go with one that has a prime number, the less you have to factor. It really doesn't matter which two numbers you choose. You could do 1 and 180. You could do 12 and 15. It really doesn't matter. So let's say I was doing 12 and 15. I know 12 times 15 gives me 180. Now I need to think of what times what gives me 12. Well, I know that's 4 and 3 and 6 and 2. It doesn't matter. For 15 we know that's 5 and 3. Then 3 and 5 and 3 are all primes, but we can factor 4 again to get 2 and 2. Then we're looking for pairs. So we have a pair of 2s and a pair of 3s. So we have 1 2 that comes out, 1 3 that comes out, because this is talking about there's one group of 3, or one pair of 3s, one pair of 2s, and then 1 5 that stays in, and you would still end up with 6 times the square root of 5.
Okay, now let's try one that's a little different than the one we just tried. So number 10, when we're looking at it, we have a number on the outside of the square root, which means eventually we're going to multiply by 2. First, let's go ahead and simplify. So if you're doing it the method where you find the highest square root that goes into it, or I'm sorry, perfect square that goes into it, 9 would work. I feel like there's something higher. Okay, we can go with 9. So we have 2 times the square root of 9 times the square root of 6. We have 2 times 3 times the square root of 6. If we broke 6 down further, we have 2 times 3. Neither is a pair, so neither would come out. So 6 times the square root of 6 would be our final answer there. If we were doing it the other way, where we're just breaking it down, so we have 2 times the square root of 54. Let's say we still use 9 and 6, but then we break it down completely. So 3 times 3 gives us 9. 2 times 3 gives us 6. We have a pair of 3s that are going to come out. So we have 2 times 3 on the outside, and then 2 and 3 on the inside, which would leave us with 6 times the square root of 6. Okay. Moving on to the next page, let's do another one of those examples. Let's do number 11. So now we have a negative out front. So if we do negative 5 times the square root of 150, breaking it down by square roots, we can do 25 for sure. Yeah. So the square root of 25 times the square root of 6. So that will give us negative 5. The square root of 25 is 5 times 6. So negative 25 times the square root of 6. 6 can't be broken down more. If we were to do it using the method where we break it down, let's say you weren't thinking 25 and 6 and we said 15 and 10. Okay, think of numbers that multiply to be each. We have 5 and 3 and 5 and 2. Even though the 5s are on different or are coming from different factors, we still have a group of 5. So we're going to bring down the negative 5 from the beginning, take out 1 5, and then on the inside we have a 3 and a 2. So that would say negative 25 times the square root of 6. Alright. So we've talked about how to simplify perfect squares or square roots. Now we're going to do perfect cubes. So just like you would find perfect squares, multiplying 1 times 1, 2 times 2, and so on and so forth, you're going to do the same thing, but you're thinking 1 times 1 times 1, or 1 to the third, which is just 1. 2 to the third, I didn't mean to put 2, which is 8. 3 to the third, which is 27. 4 to the third, 64. 5 to the third is 125. See how these numbers get big real fast. 6 to the third is 216. 7 to the third, I want to say that's 243. No, it's 343. 8 to the third is 512. And 9 to the third is 729. And then 10 to the third is 1,000. So the first 10 are really good to know, but then you get big and you do have your calculator, so don't feel like you have to know them. Right? So if you're given, if you're given a perfect square root, so like number 17, I'm sorry, number 8 is a perfect, 17 is 2, but it has a negative. The negative doesn't mean anything with your cube roots. It does for square roots because we can't have a negative underneath the square root. But for cube roots, that doesn't mean anything. We can take the negative out when we find the perfect cube. So we know 3 to the third is 27. So if we make this negative 3, that would equal. And on your calculator, you could do negative 3 to the third and you would get negative 27, whether in parentheses or not in parentheses. It wouldn't matter. Right? 18, 1,000 is a perfect square. The negative doesn't matter, so we know that inside is going to be negative 10, and we would multiply that by 2. So the answer to this would be negative 20. But if we have non-perfect cube roots, basically we're doing the same thing we were doing for the square roots. The only thing that's different is we now need perfect cubes or groups of 3, depending on how we're doing this. So let's start with number 19. 40 is not one of our perfect cubes. We can go back and look. It falls between 3 to the third and 4 to the third. So if we're breaking it down by perfect cubes, we would think of the highest number that is a perfect cube that we can divide it by. So 64 is out, 27 is out, 8, we can divide 40 by 8. So we can say this is the cube root of 8 and the cube root of 5, because 5 times 8 gives us 40. We know the cube root of 8 is a perfect cube, and that would be 2. So we can say this is 2 times the cube root of 5. We can't do the cube root of 5 without getting a decimal, so that would be our answer. However, if you were breaking it down, let's say we know this is the cube root of 40. Let's say we're just looking for factors, so that part has not changed. So let's say I do 20 and 2. Because it is a cube root, we're looking for groups of 3. So we have to keep breaking down 20. So we know 4 and 5. 4 is 2 and 2. Well, now I have groups of 2s. I'm sorry, we have a group of 3 that is 2s. And we only have one group of 2 that comes out. So that 2 would come out, and we're left inside just the 5. And you would get the same thing. Okay. Let's jump to number 20. 192 is not one of our perfect cubes, so we can start dividing. 125 is too close to 192, so that wouldn't work. Let's try 64. So I'm just doing this in my calculator. 192 divided by 64, that gives us 3, so that works. So we can do the cube root of 64 and the cube root of 3. The cube root of 64 is 4, and then the cube root of 3 would not simplify. So that would be our final answer. If we were breaking this down using factors, now 192 is a bigger factor, so you have to be careful with this one. But let's say 192 divided by 2. Let's say we don't know any other factors, and we're just going to start with 2 because we know it's even. So we have 2 and 96. 96 can be divided by 2. We have 2 and 48. 48 can be divided by 2 or other things. 2 and 24. So we have a group of 2, but we have to keep breaking it down 24. So with 24, we do 2 and 12, 4 and 6, 8 and 3. Doesn't really matter. Let's do 4 and 6. All right, and then break those down again. We have 2 and 2, and 2 and 3. We have another group of 2. So now we have 2 groups of 2. So let's do this. We have 1, 2 that would come from this one, and 1, 2 that would come from this one. Then we have to look at what's left on the outside, which would be, fix this because it didn't look like a 4. That was a 4. The only thing left at the factored level is 3. That would be on the inside. So we have 4 times the cube root of 3. So it's a longer process if you do it that way, but you can still get to that final answer if you do it that way. All right. Now let's do a couple examples where we have some negatives. So for 22, we have negative 250, which is not one of our perfect cubes, but 125 is. So I can definitely do negative 2 times the cube root of negative 125. Put the negative with whichever is a perfect cube, so it comes out, and then multiply that by the cube root of 2. The cube root of negative 125 would be negative 2 times negative 5 times the cube root of 2. Then we'd have positive 10 times the cube root of 2. Okay. And then to do the factoring method, or to find the factors, we can still use 125 and 2, 25 and 10 would also work, so I'm going to start there. It's negative. So one of these would need to be negative. Let's say I do negative 25 and negative 10. That means this would be negative 5 and positive 5. And then we have a 5 and a 2. Even though we don't have a group of negative 5s, that's okay. We just need to bring out that negative. If you wanted to, you could make this positive and say there's a negative 1 next to it. That way you know you're still taking out a negative, and we know we're taking out one group of 5s. So then we have 5 times the negative 1 times the cube root of 2, so negative 5. Oh, I forgot the negative 2 up front. Okay, and that would still give us our positive 10 times the cube root of 2. Okay, moving on to number 23, we have 8 and 96. 96 should look familiar because we just did that one with 92. So 96, if we're doing cube root, we can try 27 divided by 27. No, that's a decimal. 96 divided by 8. That would work. We have the 8 out in front. We have cube root of negative 8 times the cube root of 12. Right? Then we break this down, so we have 8 times negative 2. Now, if you're thinking 12 can be broken down, yes, it can. But the way you're going to break it down is not going to give you a group, because 12 would give you 3 times 4. And then 4 would give you 2 times 2, but you don't have a group of 3, you have a group of 2. So that would not help you. So you'd have negative 16 times the cube root of 12. But let's do it the factoring method. We have negative 96, or you can think about it as 96 times negative 1. Let's say we do 8 and 12. And we have 4 and 2, 4 and 3, and then we have 2 and 2, 2 and 2 again. So we have one group of 2 that comes out, and that's it. So the 2 will come out next to the 8 that was already there. We're still multiplying it by negative 1. And then what's on the inside is 2 times 2 times 3. We have negative 16 times the cube root of 2 times 2 is 4 times 3 is 12. So either way you look at that, you're going to get the same answer. Moving on. Now we're going to talk about what happens when we have variables. So let me go to this next page so you can see what this first part is. Okay, so if we have some radicand underneath the radical and m, the exponent, is a multiple of 2, so 2, 4, 6, 8, then we're going to use this rule. We can divide whatever this m is by 2. So if it's 4, divided by 2. If it's 6, divided by 2. Whatever that is, it's going to have a group of 2. So we're going to be fine with that. The problem is if it's not a multiple of 2. Now this right here looks weird, so I'm going to talk through it. But if we don't, we're going to break it apart. So whatever this is, subtract 1. So let's say it's not a multiple of 2, it's some odd number. Let's say it's 3. Subtract 1. So now it's at 2. So that set of 2 would be a multiple that we can go back and use this rule. But we can't just get rid of the one we subtracted. We still have to include it. And it's just going to be left underneath there. Now, talking through that probably did not sound helpful, but let's do a few and then it'll start to make sense. So for number 1, this has a multiple of 2. That means we're going to take this and divide it by 2, which would be 1. That means our answer would be x to the first, or just x. Another way I like to think about this is what times what would give us x squared. I know this is a little ahead because we haven't talked about exponent rules, but we will get there. And x times x would give us x squared. That is a group that would get to come out, and nothing would be left. You could also think about this as, think about there's an imaginary 2 inside. 2 goes into the exponent of this 2 how many times? Once. And if it's just once, then x would have an exponent of just 1. Okay, so let's try this a different way. For number 2, we have a 9 here, so that would mean we need to take the square root of 9. We know that, it's 3. Okay, now let's deal with the 10. 10 is a multiple of 2. 10 divided by 2 is 5. So we have 3 from the square root of 9, and then k to the 5th. If we were doing it using the light blue method I used in number 1, we know this would be like your factoring method, right? This would be 3 times 3, and then for k to the 10th, we have a bunch of k's. And we can see how many groups could we take out. So we have a group of 3s, 1, 2, 3, 4, 5 groups of k's that would get to come out. And that would be similar to 3, it would be the same as 3k to the 5th. And then if you're thinking about it as the pink method, you would do, okay, the square root of 9 is 3, so that would be that. This is an exponent of 2, or the square root of 2. 2 goes into 10 5 times with nothing left over. So however you see that best, do that. Let's get to number 4. So now we have 40, which is not one of our perfect squares, and 19, which is not a multiple of 2. So they're throwing double at us. All right, so that means we have to break down 40 and break down 19. So you could do a mixture of things. You could break it down using factors. You could do the square root test. So many different things. So let's say I do my factors. Let's keep the colors consistent. So I know 8 and 5 give me 40, and I can break down 8 to be 2 and 4, and 2 and 2. I have a group of 2s that gets to come out. And that's it. For your A's, I don't want to write out 19 A's. So instead of using my factoring method for that, I'm going to think about, okay, 2 goes into 19, how many times? 9. With 1 left over. Right? That's how you would think about that. So when I write this final answer, I know I have one group of 2 that comes out, and I know that 9 of the A's are going to come out. Let's color code. So we know this, we know this. What happens to everything else? So on the inside of the square root, we still have 1, 2, and 1, 5. And then we know that there's still one A left over inside. So when we write our final answer, it would be 2A to the 9th times the square root of 10 times A. I know that probably was super confusing, but we're going to do a couple more problems like that. Right, starting with number 5. So with 5, 25 is a perfect square. So we know that's going to be 5 and 5. That's going to be a group that comes out. 6 is an even number. So I know that 6 divided by 2 equals 3, so there's going to be 3 x's that get to come out. Y is not a even number. So if I think about 2 goes into 13 6 times, there would be 1 left over. So putting all of that together, we would have 5 come out, 3 x's come out, and then we would have 6 y's, but there would still be 1 left underneath this square root. Now, could I have written everything out using factor form? So x times x times x. Okay. So we know the group of 5 came out already. There would be 3 groups of x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 6 groups of y's with 1 left over. So you could do it like that. It's really your preference, but we probably won't use the same method for each one. And you have to know that. Right, let's move on to number 10. Right, so now we have numbers outside, and we need to simplify. So I'm going to go back to the square root method. 180 divided by the highest square root. I know it's not 81. Let's see, 64, that wouldn't work. 49, that wouldn't work. 36, that works. So I know square root of 36 times the square root of 5. 2 is even. So I know there's going to be 1 u that comes out. B is a power of 1. 2 does not go into 1 at all. So that means B is going to stay on the inside. So what I have so far is the original negative 2 from the outside. The square root of 36 is 6. On the inside of that, I have the 5. Let me space this out. Well, I'll write it as is and then we'll rearrange. We know there's going to be 1 u that comes out, and then there's going to be 1 square root of b that stays inside. So if I rearrange all of that, I have negative 12 u times the square root of 5b. It cannot be simplified anymore, and that would be our final answer. All right, let's do one more of these, and then we'll move on to cube roots. Okay, 144 is a perfect square. We know that to be 12. I'm not going to go through the factors. 16 is an even number, so if we divide that by 2, we have x to the 8th. 10 is an even number, so if we divide that by 2, we have y to the 5th. Z is not an even number, so 2 goes into 7 3 times with 1 left over. So we have z to the 3rd that comes out with 1 z left over. We have negative 5 times 12 times x to the 8th, y to the 5th, z to the 3rd. On the inside of that, we have z. So the last thing we have to do is multiply. So we have negative 60 x to the 8th, y to the 5th, z to the 3rd times the square root of z. Alright, let's move on to cube roots so we can be done with all of these. So just like our rule for square roots, this is similar. Show it really fast. If it's a multiple of 3 now, we can divide by 3. If it's not a multiple of 3, we have to change it so that it is, just like we had to for the square root. Okay? I've shown way too much. Right. So let's start with number 13. This is a multiple of 3. So that means 3 divided by 3 is 1. That means there's going to be 1 x that comes out, and our final answer is going to be x. You can also think about that like what times what will give us x to the 3rd, which would be x times x times x. We're looking for groups of 3 to come out, which would mean 1x comes out. And then the very last method you can think about, there actually is a 3 there, so 3 goes into 3 once, and that would be 1 exponent. Right? For 14, we have the cube root of 64, which is 4, and we have m to the 9th. So if we divide that by 3, that is 3. So we have x to the 3rd, and 4x to the 3rd would be our final answer. Now, if that went too fast, we can do it a different way. So we could think about, we know 4 times 4 times 4 is 64. And then if we had all of our m's, we have 1 group of 4s and 3 groups of m's. So all of those would come out of the radical, and there would be nothing left inside. And then the last way, 3 goes into 9 3 times. So that would be an exponent of 3. And then we'd have to simplify the 64. Right? Number 17. 512 is one of your perfect squares. That is 8, I think. Yeah. X has a power of 1. That does not go into 3. Can't be a multiple of 3, so that's going to end up staying inside. And I'm going to just skip to the last one, last method. 3 goes into 10 3 times with 1 left over. So we have an exponent of 3 that comes out with 1 left inside. I'm sorry, this should be a y. And we know this 1 by itself is also going to stay inside. So 8xy, I'm going to rewrite it. Y to the 3rd times the cube root of xy would be our final answer. Skip down to 19. Now we have 32. 32 is not one of our perfect cubes, but we could divide it by 8 and 4. Right, and I'm going to do our last method for our variables. Oh, let me finish this first. So we know this would be negative 2. I cannot break down the cube root of 4 anymore. And then 3 goes into 17. Let's see. 3 times 6 is 18, so that's not it. 3 times 5 is 15, so it goes in 5 times with 2 left over. And then 3 goes into 8 twice with 2 left over. So this would be p to the 5th and q to the 2nd. And then on the inside left over, we have p squared and q squared. So putting all that together, we have something that looks like this. I'm going to rearrange these as well. So -2 is the only number on the outside. P to the 5th comes out. Q squared comes out. On the inside, we have the cube root of 4, p squared, q squared. There is nothing else we can divide out of that. That would be groups of 3. So that would be our final answer. All right, we're going to do 2 more of these and then we'll be done. I know this video is getting really long. I'm sorry. All right, 128 can be divided by 64. We have the cube root of 64, the cube root of 2. 3 goes into 9 3 times, so that would give us a to the 3rd. 3 goes into 21 7 times, so that would give us b to the 7th. So there will be no leftover a and b inside, but there will be a leftover number on the inside. So we have the 3 from the outside originally. The cube root of 64 becomes 4, so that would come out. And then our a to the 3rd, b to the 7th would come out, and the only thing left would be the cube root of 2. Putting that all together, we would have 12 a to the 3rd, b to the 7th times the cube root of 2. Right? And then for 21, for 48, we would have to divide by 8. So we have the cube root of 8, the cube root of 6. 3 does not go into 1, so this would be a standalone something on the inside. 3 goes into 9 3 times, so that would be y to the 3rd on the outside. 3 goes into 5 once, with 2 left over. So we have z to the 1st come out, and z squared stay in. -8, the cube root of -8 would be -2. So we have our original 7 times -2. Things that come out would be y to the 3rd and z. And then on the inside of the cube root, we would have 6, we would have x, and z squared. And then simplifying all of that together, -14, y to the 3rd, z to, not the 3rd, sorry, that's the cube root of 6x z squared. I know that was a lot of information. Please come see me if you have any questions on any of this. We can go over all of these together. Let me know if you have any questions, but use this time and go practice.